All right, good. So, good. Let's open the browser. Let's go to Moodle. Let's wait. Okay, here we go. And very down here, there is this software assignment story. Okay, so due date, idea behind. So what do we want to do in general? So the idea is that we will use so-called wave DAC, and the DAC is just the opposite of an ADC. An ADC is converting an analog voltage to digital data, while a DAC is converting digital data to an analog system, analog signal that way. And so we want to use this wave DAC to create a voltage. We want to give it to a so-called DUT, device under test. Bring that voltage into that circuitry and then use an ADC on the other side to measure the output again. And then we want to simply analyze what the circuitry is doing. Yeah? So this is our stimulus, and on the other side, we capture the data again. In the first step, what we will do is that we will test the test bench. So the idea here is by just introducing a voltage divider, we want to simply see if we bring some signal here, yeah, to the device under test, then if the ADC data makes sense. Yeah? Because for a voltage divider, this is comparable easy. Simply the voltage will be lower by the factor of the voltage divider. So this way we can very simply check if our application is working. And once this is done, I think this will be a next step. I don't think this is this assignment right now. We want to bring in the operational amplifier, yeah, so the bandpass filter in here, and then use this test bench here. Everything which is like bluish here, this is our test bench, and we want to check if our bandpass filter is working. Yeah? We started with the voltage divider, we continue that to the bandpass filter. So that's basically the main objective, what we want to do here. Good. So first of all, there is this MATLAB script. I would propose that we dig into that a little later, that we first will focus a little bit on the exercise itself and then the components in PSOC. And once we understood all that, then we can have a look at the script and what it is doing. And I already also opened it so that we can investigate it a little deeper. Good. The aim, I'll just mute you, or do you have a question? Okay, then I mute some guys. So the aim is to use the DAC, digital analog converter, for example, the waveform DAC, which provides the test signal. And we want to use a 16-bit sigma delta or ADC to sample the voltage divider output and store the samples in the SRAM, so simply in a global variable, by using the DMA. Okay, so we also will talk a little bit about DMA. If MATLAB requests, send the ADC sample data from SRAM by UART to MATLAB. Okay, good. Any questions about that so far? Good. So let's start PSOC Creator. I will also make sure I have my scope connected, because then we can also look at the signal.
Professor, the idea of using MATLAB is just to visualize the ADC sample data, right?
Exactly. Exactly. And later on, I think this will be one extension. I think Professor Banvard also wants to do a fast Fourier transfer, so an FFT. And then the nice thing is you can do it once on the PSOC, and you can do it once on MATLAB, and then you can compare if your FFT is working correctly. Yeah? But the main purpose for now is with MATLAB simply to visualize the data.
Okay.
Good. So where is my creator? There it is. Okay, well, let's create a new project. So we make sure that our target device is correct. I also will make sure that I have it on my desk. Oh, and I forgot that I have to do this twice. So I need to get those pin headers again so that I can hook up my scope. 2 of them. Then I also need a probe for my scope. My old school scope. All right, and let's already switch that on so it can warm up. Good. So this is the target we want to use. We will start from scratch with an empty schematic. New workspace, yeah, maybe, I don't know. Test bench. Get started. Okay. Yeah, I don't know if you can see that, but Windows has some problems because I have 2 monitors and one is a 4K monitor and totally messes up with some graphic effects here. Good. Anyhow, so we need a deck. So in general, there are 2 flavors of decks. There are decks which can provide a certain current. Yeah, so the input you give in here is not the voltage, but the current you want to have. Or you can have a voltage deck. Yeah, so it's providing a voltage. Then there are 2 special forms of that. There's this dithered deck. The idea here is, as far as I understood it, it will very quickly oscillate between 2 levels, and that way it will kind of simulate a higher resolution than it actually has. But this is not really interesting for us right now. And there is this waveform deck, and maybe let's have a look at that guy because I think that's interesting. So we'll simply drop it in here, and I already will connect a pin to it. Because we want to leave the analog circuitry here and want to go off chip so that we can measure it with a scope. So we will need an analog pin for that. And for the analog pins, you do not have input or output pins. And we could still hook that up, but you can also say, I want to flip horizontally this symbol, and then we can connect it to the deck. Okay, I'll already also do the pin assignment. And here you have to be a little bit careful, and you should reuse those or use those constraints here. Why is that? There are certain pins on the FreeSock board which have special purposes, and for this special purpose, for example, they are connected to a capacitor or something, and of course this would now mess with the behavior, so we cannot really have like the pure pin state. So please stick to those constraints here because those pins are tested, I hope. So 15.5 is the pin we should use. Okay, and while we investigate all the internals, I'll give it already a first build. Okay, there's something not connected. Okay, then let's go in here. I'll rename that so it is a little easier for me to use the API of it. So what is a wave deck? A wave deck basically is a macro or an already made or a library component which makes use of the underlying deck and brings in some application code, some logic. And what a wave deck is providing is that we can very nicely with a GUI simply define the waveform we want to see at the output. And there is some software auto-generated which will automatically feed this deck with data so that it creates the signal we want to have. And one thing I like here very much is that you can draw stuff. So, and what I really like to do is to draw, maybe you encounter what it is. Yes, you're damn right. This is the Batman signal. So we'll go and try to see our Batman signal on the scope. I'm not happy with that. Sometimes I'm a little childish. I think that's fine. Maybe like that. Okay, perfect. So the idea here is you can also give sine waves. If you give the sine wave, then you can set an offset and so forth and so forth. And I'll focus on that in a second. Good. So we can use simply this, this small GUI here to create, for example, a sine wave, which will make sense later on if we talk about our bandpass filter, because then we can check the characteristics of the bandpass filter. What we also can do in here is to select the range. And again, there are a lot of different settings here. I actually would have to check the datasheet what's the difference between the buffered and non-buffered. We can also do that in a second. But for our voltage deck, there are basically just two options. We can go from 0 to 1 volt or from 0 to 4 volt. And well, for our application, we'll also select this 4 volt. Why do we have this possibility to check or to change that? Think about it. The deck has a fixed so-called slew rate. And so the slew rate is the change of voltage over time. And this is just, there is a maximum for that, how fast it can change the voltage at the output. And if you shrink that down to just a volt, right, then this can be way faster, or the slew rate is then comparable good, yeah, and you can very fast make those curves, and you can later on, for example, use an op-amp to simply amplify that. Yeah? If you have the full swing, then the slew rate remains the same, so it might be possible that the output is not fast enough to create that signal. So that's the story a little bit in here. Good. But that's basically everything we need to do here. Now it complained a little bit about this terminal WS is not connected. So let's have a look what this is doing. And we see here the wave select input selects which waveform will be generated. It can be used to switch quickly between two waveforms to create an FSK signal. So frequency shift key, I would assume. So we can use this to also generate some radio signal, for example. But for us now, we just want to use the upper waveform. So we can give it a constant. We can use a digital constant like that here, or I'll simply say, no, it's low. Okay, then let's try if we can compile that. In the meantime, I'll already connect the pins here. 15.5. Oh, build succeeded. Yes, yes. Just connecting the scope. Good. Also, what we need to do in here is to wave deck 8, just to start it once. So we'll flash it. In the meantime, I will search for my scope thingy toolie here and hope that it will connect. This is looking good. Let's zoom a little bit. Okay, so this was programmed and we cannot see anything here. Ooh. Let's see. Auto always does the trick, right? Ah, there it is. Yeah, see, and we have our Batman signal. Cool. All right, so let's now get a little bit more serious and let's talk about the waveform we can generate with that. Maybe first of all, we want to see this, what this buffered means. Well, I'll leave that up to you to find out what it means. I have no idea. Good. So, but what is more important for us now is to say, okay, we want to have a sine wave. And we know that our sine wave, actually we can go for this scale here, has an offset of 300 millivolt. And then let's say, for example, it should have an amplitude of, or voltage peak to peak of 100 millivolt, something like that, okay? And also, and now we need to do a little math. So if we have 100 samples for that, and our sample rate is 100 kilosamples, then we will end up in a range of 100 kilohertz. I would say 100 samples here for that sine is pretty good. So we can reduce, if we, let's say, for example, want to have 100 hertz, so which is approximately in the magnitude we talk about for our radar sensor, then we'll simply make that 10. So we end up with 100 hertz. Okay, let's simply try that. Okay, this doesn't work. Okay. Let's go for auto again, because the usability here is a pain in the butt. Okay, good. So then let's move the position here a little bit. Oh yeah. Oh my God. I can see on my scope that it's doing it, but it's horribly slow. Okay, and then let's maybe measure all that a little bit. Simply display all. And is this the right button? Yeah. Good. So let's have a look. We have a frequency of 100 hertz approximately. That's fine. Our average voltage is around 300 millivolt, and our peak is 114 in that case. Yeah. So it overshoots a little bit, but that's not too bad. So as you can see, what you see is what you get. You can simply use this wave deck and the configuration here to generate a signal, okay? And of course, you can now here rather static configure that, yeah? But it might be interesting, for example, if you implement something like a bandpass filter so that you play around with the frequency of that. And to do that, there are different ways on how to do that. You could, for example, say, well, I generate an external clock, and you have to think about a little bit what you can attach to this clock so that it, this clock is not constant but will change a little bit. This is one way to go. Another way to go might be, but I have not checked that, to read a little bit through this data sheet here and check the functions which are available, because there's also this set speed, though this might be maybe the slew rate. Yeah, this is slew rate. So this will not really help. But you might want to check if you can on the fly, for example, use this here or whatever to sweep the frequency. Yeah, so but I'll leave that a little bit up to you. Good. Questions so far about the wave deck?
Professor, for the current software thing, it's basically necessary to generate a sine wave and just reproduce it in the using the ADC, or is there any specification regarding what kind of sine waves to be generated and something like that?
Yeah, so we had this discussion also yesterday. You might want to ask Professor Banvard about that, but there's nothing said about that here. Yeah. Not a single word. Yeah. So for the assumption I have, like for me, it would be okay, but we have to just discuss that also internally. But I don't think this will go somewhere else. I will check the values you have given here, right, and then have a small test bench also here. With the two 1 kilo ohm resistors, so basically having a voltage divider, and I will simply check in MATLAB if like the voltage you described here is just half in MATLAB, and if I can see it.
Okay.
And then I maybe I'll play around a little bit with that, change something here. I don't know, we'll see. Good, good. I mean, like, of course, you can use the wave deck, yeah, so then it comes everything out of the box, or of course, you could also use the just the voltage deck and then manually feed it with data. So this is up to you. No, I'm just showing the possibilities here. Okay, good. There is now somebody on the door, and I need to pause for just a second. I'll be back in a second. Sorry. Okay, sorry again. Good. Can we continue for DMA?
Yes, Professor.
Okay, good, great. So let's do the following. Let's bring in a UART module, and we will just have our basic configuration of that. We need to do the pin assignment. Let me check. 2, 0 is RX, and 2, 1 should be TX. Okay, let's compile that and try if this works. Oh shit, I need that. Okay. Yeah, maybe let's have it that way. Okay, and then as a test bench to simply make sure, like this is my recommendation, whenever you bring in a new component, we make sure that it works, okay? And to make sure that it works, I'll do the following. I say, I want to have an interrupt fired every time there's a new byte available. That's IRQ UART. I should now need to compile that again. And every time I receive the byte, so the interrupt gets fired, I want to have this ISR executed. And in here, I will simply loop back the byte I just received. Okay? So now we also need to hook up this UART Sdhd. Okay, good. Now, very important. What I just did, is this clear to everybody? I cannot split that up, but what is happening here? Yeah, so we get a new byte. The RX interrupt will be fired, so it will stop our code, whatever we are doing. We'll jump to the ISR, we'll perform that. Once this is done, it will return to whatever we have just done. Is this clear to everybody? Like, just if there is some doubt, then please shout. Very nice. Okay, then I'll do just very briefly some theory about that. If I find the file, some of you guys might already be familiar with those slides. So, so as I just said, what is happening is we have our normal program. Now the interrupt happens. We're now on this ISR, and then we return. If we think about that now on a bus level, then this means, for example, here our serial line is triggering the CPU. The CPU stops its execution, goes into the ISR, and what we do in here, get byte put char, what it will do internally is to read out the data from here, load it into the CPU registers or RAM, and then push it back out to serial. I think I already did that also with you guys, that I created here this this buffer, and then use the ISR to write data in it, right?
Yes, Professor.
Yeah. So in that way, actually, the storyline would be a little different. UART notifies via an interrupt the CPU that there is something available. We read the data out from the serial and put it into RAM. Yeah. Good. This is one way to do it. But the problem here is that every time we receive a new byte in our CAN module, the CPU gets involved. Yeah, and the CPU, the job of the CPU is to execute our software, and we're simply losing time. Now we could use that time for something else. And this is now the situation where DMA, direct memory access, comes into play, because DMA is also, like it's not shown here, it's also a peripheral or something which is attached to the bus, and something where we can hook up interrupts to. And this DMA controller, it's very stupid, but what we can do with it is to say, please take the information out of the serial and put it directly into RAM. So bypassing the CPU. Okay, so that's the basic idea of DMA. So for example, I remember one of my first computers, PC, IBM compatible computers, when DMA became available, then suddenly it was way faster to store something from disk or from CD-ROM to the hard drive. Yeah, because it was simply bypassing the CPU. Yeah? So the CPU was available for me to move around my mouse or do whatever, yeah, while that stuff happened in the background. So that's a little bit the idea here why we want to use it. Unfortunately, and this is also the reason why I usually don't use it too much if I don't have to, the configuration is a little bit painful. I mean, like on PSOC, it's a little easier, but still it's painful. But let's do it. So first of all, the thing we need here is this DMA component. No? Okay, I'll just rename it to DMA, or let's say DMA UART. And what we need to configure here is that we want to have hardware requests. So the idea here now is that we want to trigger DMA transfers whenever there is, for example, new data available. So I'm right now doing this with UART. You will later on do this with your ADC. Now, this is a little bit the idea, but I cannot show it now with the ADC because then you could simply copy paste it, right? So I'll do it now with a UART, okay? And this is the input of the DMA. So whenever there's a new byte received, we will trigger this DMA. It will do the byte transfer from the UART module into our memory. And then there is this NRQ output. I mean, like, of course, you can, as always, check all that in the in the data sheet what they are doing, but I'll just do it here a little fast forward so that we can get through. This input or this output here will create a trigger once the DMA transfer has finished. Okay, what does it mean? The transfer, the data transfer has finished. We can configure it in such a way that this is not the case for every byte which is transmitted, but let's say, for example, for every 100 bytes. No? So we need a way to configure the DMA here a little bit more precisely, because, for example, what we want to do is that in the memory where it is storing, so in this UART buffer, for example, we cannot write to the same address all the time, but we need to increase the index with every byte we receive. And all this logic, like those rules, this is a so-called transport descriptor. Okay. I know. Let's do it slowly. So there is this DMA wizard under tools. It's not perfect, but it can help us a little bit. Good. So we're in that project and we want to use this DMA UART. I will leave certain things here as default, or maybe let's leave all that because this DMA wizard will simply generate some code which we have to insert in our main file or wherever. It just creates an outline or a template, and I will simply modify that. So I do not care too much about that here. Good, but we can talk a little bit about this stuff. So we want to have this TRQ enabled. I think this is this story here, that if the transfer is terminated, we want to have our UART. What is this, NRQ? I don't know. Let's say the overall length should be 100. The source, this is very interesting. I hope I cannot, okay. So we need to define where our data is coming from. Is there still the ADC? No. I already know, because I did that just yesterday, that in the data sheet of the UART, there is a register defined from which we can read the data, the RX data, but I don't know it yet, but so I'll simply first insert here as kind of a placeholder. We do not need to increment this address, this source address. It will always be the same register from what we're reading, okay? The destination now is our UART buffer. I don't know the name and I cannot go to it, so I'll simply write UART buff. And here, actually, we want to increment, right? Because with every byte we receive, we want to increment the address so that it goes higher. And I think that's already it for this wizard. It will produce terribly ugly code, and we will simply modify that a little bit. Good. So first thing now, I check before I go deeper in here. So I know that this here will be my destination. Those are the number of bytes we want to buffer. And let's now also check a little bit where our source is. We can open that. You see it's already open. So what I did here is I searched for DMA and I ended up at this page, and down here I can see that this is the actual address of the UART module where I can read my data from. So this will be our source. Good. I don't like all those defines, so I'll just delete them. I will do that manually, step by step. We need some global variables for this UART stuff. There is this channel, whatever it is doing, and there is this transport descriptor, which will contain the cat video. Yes, there was a cat video. And this is this transport descriptor. We could have multiple, that's why we have an array, but for our application now, we will just have a single transport descriptor, so it's only one. Okay, now let's take this huge ugly block and we will put it maybe down here, and with the help of our best friend, the data sheet, we will go through that entire configuration and see step by step what is going on. Good. First thing, I think we first need to compile that because it doesn't find this function here. Okay, now it has found it. Okay, let's first have a look at this DMA initialize and what this is doing. Your phone is ringing. So let's search for DMA initialize. Is it in here? Oh. Here it is. API per DMA instant, DMA initialize. Allocates and initializes a DMA channel to be used by the caller. Okay, let's simply already copy this bit of information that we see what's going on. Good. First parameter. It's the burst count. Specifies the size of burst, so 1 to 125 bytes, into which transport descriptors on this channel should be divided. The burst size should be multiples of the spoken size. If this value is 0, each transfer is done as a single burst. In this case, the transfer count parameter for each transport descriptor determines the number of bytes to transfer in one burst. Blah, 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 blah. I have not understood a single word what they're talking about. But from experience, I know, or from because I simply tried it, that this is the number of bytes to transmit per request. Yeah, so this is what it's doing. Okay, then for the next parameter, requests per burst, okay, there are two values. One is all subsequent bursts after the first burst will be automatically requested and carried out. Or all subsequent bursts of the first burst must also be individually requested. Yes, this is what we want. So for every request there is, for every byte, we want to have one burst. Yeah, so that's the general idea here. Okay, so we want manual, or one means mode, automatic requests, and one is manual requests. Okay.
Professor,
yes.
I just have one question in this. So for example, if you want to transfer 4 bytes, like a UN32 data, still the number of bursts should be 1?
No, then you would have 4.
4. And for every byte of the 4 bytes, we will have a burst sent, like the second configuration mode.
Yeah, this means that it is not like, okay, we trigger it once and then it will automatically do this 100 times, but it means that for every request, we will just do this or copy this number of bytes.
Okay.
And at least this is how I understood it. Yeah, so maybe it's a little different and you have to check it, but this is how I understood it. Yeah. But I mean, like, this is why I also do this example. I think it makes sense that you maybe use this as a template, and from there, because there you can play around with parameters and check what it's doing, okay? And once you're confident with that, then you can extend it and bring in the ADC. Yeah.
Okay.
Okay, so this is the upper source address. And this is the lower destination address. So how this works with DMA is that the DMA module holds the upper portion, so the first 2 bytes of the address, while the transport descriptor, so the more or less variable configuration, contains the lower bytes. So this is now simply a hardware specific configuration, and I assume like they do it for performance reasons, to split that up a little bit. So always think about it. We configure here this module, and this module can be fed with multiple configurations, and those configurations are called transport descriptors. And one part of the configuration is done in the module, the other part is done lower in the transport descriptor. Good. So the source address, let's do this. Very beautiful. It's our UART source rec. Come on, screw it. We'll simply use this one. So, yeah, here our data is coming from. Remember, I looked that up in the data sheet. This is the register for where the RX data lives. And the destination is this guy. So why can I paste this directly in here? Because the name of an array is
address of an array.
exactly the address of the first element or the 0 element. Yeah. So this actually is a pointer. Yeah. And so I can simply insert it in here. And what this magic high 16 here is doing, it will simply shift the address value by 16 bits so that we get the higher portion, and only the first 2 bytes of the 4-byte address. Okay. So this magic statement here will do an allocation of this transport descriptor, whatever this means, but it will create some handle and store it in here. Yeah, so allocate transport descriptor. Yeah. So I'm not sure.
Professor?
Yes.
Do we need to worry about Indianness of data here?
Not really. Not really. Or you mean for the later on, if you have 32 bytes or 16 bits, it's possible that you have to care about the endiness there. But I think we will stumble on that if we go now to this configuration. I think there should be something in here. We'll see. We'll see. But yes, this is a very good point. Okay, now we need to check where we get the documentation again for this SciDMA set configuration. Because there is this Sci in front of it, I think this is not really, you know, a function which comes from a particular hardware module, but from the overall ecosystem. And to check the overall ecosystem, I can right-click here on an empty space here and say I want to open this SciBoot datasheet. And this is basically now not the datasheet of an individual component, but a system documentation, more or less. Yeah. So let's see if we are lucky and can find it in here. I found it yesterday, though, but I have no idea. Oh, okay. So it's in here. Okay, it's not in here, but now you know that there is a file. So if you once are bored and it's raining and it's Corona and you have no idea what to do, then you can read that. Okay. So let's maybe also close this stuff. Okay, so here's this documentation for that. So let's go through all the parameters in here. So here we configure the transport descriptor. Okay, so first parameter is the handle, which was previously returned by this allocate story. Yeah. Okay. So this is our transport descriptor handle. Here we allocated it. Here we use it. Next parameter is the so-called transfer count, the size of the data transfer in bytes for this transport descriptor. Okay, you can read the documentation, what are the constraints here, but basically those are the total number of bytes we want to transmit. And I'll simply reuse that one symbol we had here, so it becomes hopefully a bit more obvious what is going on. The next transport descriptor. So how this works with those transport descriptors is that once one has finished, so for example, we have now received the first 100 bytes, then you can configure the system in such a way that it switches to the next configuration and does something else. Okay, we do not want this behavior. We only have this one transport descriptor. So we set it to SciDMA disable TD, like it is described here. It will simply disable the channel once the transport descriptor has ended. Yeah, because we also do not want to overshoot. If it would simply continue, then it would exceed the range here and continue, you know, writing in here. So the idea here is once we have received 100 bytes, we will deactivate this transport descriptor. Yeah, so this configuration. What is more important down here, and I think here you have your endedness. Yeah, but once again, extremely good point. Yeah, that you thought about that. Here we can bring in some settings on how our DMA channel should work. We can give multiple of those, and we have to separate them here with a bitwise OR. Yeah, so just a single OR. Good. So first of all here, terminate channel after TD, so transport descriptor has finished. Let's check this setting here. Terminates this transport descriptor if a positive edge on the TRQ line occurs. We do not have a TRQ line. Bye. Bye bye. Term out EN. When this transport descriptor completes, the term out signal will generate a pulse. Note that this option is instance specific with the instance name followed by 2 underscores. In this example, the instance name is DMA. No, in our implementation, it is called DMA UART, that guy, and we want to create the pulse here at the output so that our interrupt gets triggered. Yeah, so this is the configuration for that. Good. And also, we want to have this inc DST, which means that for every call or for every for every transfer, we will increment the destination address by the size defined by the burst size. Yeah. So what does this mean? We start at this address, okay, so with the first element and the buffer, and for each burst or for each transfer, we have to increment that step by step in the buffer. Later on, we'll also check a little bit how all this looks in memory. Okay, now we need to continue to set address. It's here, okay. What is it doing? It's setting the lower portion of the addresses, okay? And so here we had the upper part. And down here, we need to define the lower part. So this is again our transport descriptor handle. Now this here is the lower source address, and this here will be our upper. No, dude, come on. Also, why don't I have coffee? Like, I can't write software without coffee. Like, this is not how it works. Good. So, but as I said, the idea is as follows. In the DMA module itself, we configure the upper portion of the addresses in the transport descriptor, which is kind of the configuration, exchangeable dynamic configuration. There we have the lower part of the source and destination address. Okay. Here we set the TD to use. Yeah. So what this function will do is that it will tell our DMA module which transfer descriptor to use. So this is basically the DMA module, and now I know why we need this DMA chain thing. Okay, so this is a DMA module handle. And this is the transport descriptor to use. Okay, and this down here will simply enable the DMA channel. So this will be the, oops, wrong line. This will be the module, and I think this down here, yeah, this is the setting if we want to preserve the transport descriptor. Is this defined anywhere? Yeah. So 0 would mean when a transport descriptor is complete, the DMAC, whatever, leaves the blah, 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 TD configuration values in their current state and does not restore them to original state, while 1 means once a transport descriptor is complete, then the DMA controller, I guess, restores the original configuration values of the TD. So which makes sense that we want to restore that, because once we have ended our transfer, then for example, this count should go back to 0, so that if we enable the channel again, that it starts all over, right? Good. So restore TD config after TD has ended. Questions? Okay.
Professor,
Yes.
how will the multiple transport descriptor be used in this case? Like if you want to have more than one transport descriptor?
I've never did it. You might want to use the wizard for that.
Okay.
I don't know it right now, how to do that. Sorry.
Okay.
But I guess like here, what was this? Next TD, yeah? So if you now do the configuration of your transport descriptor, so let's start maybe from top. You would need a bigger array to store them.
Okay.
You would need to allocate for each transport descriptor. You would have to do this allocate. For each of them, you would have to give this transport descriptor set configuration. And in here, you basically define the next TD. So you can say once this has finished, you can say which one should be executed afterwards.
Okay.
And then again, for all of them, you also not only have to do the set configuration, but also to do this set address. Then you have to decide with which transport descriptor you want to start. Yeah, I assume it works somehow this way.
Okay.
Good. Are we brave? Do we want to test that? But let's bring it on to the target. Now let's start our machine, and I want to show you one thing. I'm not sure where it is right now. We can also stop it. So this is simply optimized away, and now it cannot really represent what we're doing. I'll do some magic here. I'll just insert a single assembly instruction so that I can set a breakpoint. NOP means no operation. So the CPU is basically just doing nothing. Yeah, but we can simply use that to use up time. But this gives me the possibility now to set a breakpoint here. Haha, magic. Now, but what I want to show you with that is the CPU now is stopped. But if I have a look at my scope, then I can see that the wave DAC is still working. Why is that? Okay, the CPU is stopped, but the DMA controller is still active and is pumping like our lookup table for the sign from RAM to our DAC. Yeah? So here you can really see that this is independent of the CPU. Yeah? Good. Let's have a look first of all at our UART buff. Let's add that to the watch list, and I hope that somehow I can have that side by side. Yeah. And as we can see right now, there's nothing in there. Okay, we'll continue execution, and I'll write some data in here. Okay, now let's stop. And as you can see, this information was put into this buffer. Now let's modify maybe this ISR here a little bit. And let's say the following. Once we have reached 100, then I'll simply want to give a K up here. Okay, so start the debugger maybe again. Okay, and now and now you can see we received the K. I can also have a look now at this buffer. And we can see that all the data we have received is now in this buffer. Okay, but there is a problem now, because if I continue to send data, nothing is happening. And I can also tell you that if I send this data and have a look at my buffer, it's not here. Okay, and this is because we set down here that once our transport descriptor, so our 100 bytes have finished, we want to disable this transport descriptor. So what we have to do up here is, once we have the, I mean, like, this is now a little bit up to you when you want to re-enable the system. Yeah, I'll just, for a continuous operation, will now place that into my ISR, and I say like, okay, once I have maybe received all the data, then let's maybe like do the following. I want to simply loop back that entire thing, and then I will re-enable the DMA channel. Yeah, but this is now really think about if you want to do it up here or how you want to do that. Let's try that. Yes, I love you too. Is it lost or no? It's still there. Okay, I guess I need to reconnect here too. And now let's try it. And as you can see, once it has 100, then it will loop back. Not now, but once it has 100, it will loop back everything. And it will also re-enable the DMA channel. Okay. Now let's have a look, or any questions so far about that? Good. Now let's talk a little bit about MATLAB. And one particular thing I want to show you, or before we go a little further with that, is the following. Because what MATLAB is expecting here I cannot zoom in. Okay, so I had opened it here. Maybe let's lose this one because the text is simply a little bit bigger. Is that it will use U in 16 values. Okay, so what does this mean? We want to have 16 bits from our ADC. Let's simply call that test buff, maybe also 100. And so that it doesn't get optimized away, I'll simply put it here. I just want to, oh, no. I want to do something different with that. Sorry. Because what I want to show you, I'll just fill it with some test data. So for int I equals 0, I smaller than 100, I plus plus, and I will simply insert in this array now the running variable itself. Okay, and now let's have a look at what this will do in memory. Want to put that to the watch view and start it and stop it. Okay. So in here, as we expected, okay, the index is the same as the value. It simply goes up. Good. But now let's have a look at the memory, how this looks in memory. 0x1 ff8164. Because what you can see here is, because there's a U in 16 type, then we have 2 bytes per value, right? Can also see the endianness here. Yeah. And because of that, we expect 2048 bytes, but they are only 1024 values. How to transmit that from PSOC to MATLAB? You can, for example, just use this put array. Yeah. The only thing you would have to remember, or have to be a little bit careful about here, is that you say, okay, if I want to transmit this array now, this data, then I cannot use only 100, because this would simply transmit only half of the array. What we need in here is to also tell it, okay, 100 times the size of an individual entry. Yeah, so it will just return 2, but it's better to write this instead of 2, because now it's more readable and somebody else would understand what we're doing here. Yeah, so because to transmit 100 U in 16 values, we need to multiply that by 2, because each value consists out of 2 bytes. Yeah? And this put array is expecting the byte count. Oh, I just see something. This will be interesting. I'm not sure if Professor Banwat has thought about that. It's limited to 8. It's an 8-bit byte count value, and we want to transmit later on this size, right? So this will not fit. My recommendation here, no matter what, is to increment this this buffer size here anyway to at least this size. So because this is the number of bytes we're expecting here, and why to have the hassle to deal with that? Simply say for my UART module, I have this as a buffer size. Let's see if this will change the API, because otherwise this might be a problem for you guys to implement that. Yeah. So now it's 16-bit. Okay, this is better because, so important, we need to set the buffer size here to a big value, right? So I propose to simply at least make it so big that all the data can be, pumped in a single request or a single transaction, so that also this function here accepts a higher byte count. Yeah. Good. I think I lost it somewhere, but simply ask questions if there's something not clear. Okay, I would now start to go through the script here. Okay. Okay, good. Close all should be obvious. Close all the windows. Clear all. Clear the terminal. First I have to admit I'm not an expert with MATLAB at all. I mean, like I used it twice as a student or something, and that's it. Yeah. So the rest is just like I'll try my best here to understand what it's doing. Okay, CLC. I guess this is also some default clearing story. I have not completely understood what this is doing, but it looks to me that it will delete all the prior serial ports or something like that. Yeah, but simply copy paste it. Now this is a little more interesting. Here we create a serial communication line, which we call PSOC. You of course have to make sure that the COM port here is correct. You have to make sure that the baud rate is correct, like the ones you have configured. So I have a different one now. This is up to you. You always need to make sure that it fits. Though I would propose we go for 9600 also here, because this will make testing for me way easier. Yeah. So please maybe use this baud rate. Yeah. Okay, we want to create a new figure, and there's this magic variable count, which is just as a transfer count. There is this flag, which we can use later on to determine if we still want to read data or not, and so just a variable. But more important stuff now. We will write the character S to the PSOC. Yeah. So before you do anything in your application, you first await this S. Okay. Good. Once this S is received, then there is this loop here, looping all the time until the bytes which have been received for this serial communication here, the total number of bytes is 2048. So in your application, what would that mean? Once you have this S, you start your measurement, you fill up your buffer. Once you have enough samples, then you send them out through your UART module. And then at some point, the number of bytes available here will be 2048. Then an O will be sent to the PSOC. You can use it or not, up to you. Simply to indicate, oh, I guess like this means starts, and this means like, oh, I have received all the data. I don't know. And then in the next step, it will parse all this data. Yeah, so read from the buffer, read 1024 uint16 values. So the bytes available in the buffer of the serial communication line are 2048, but because each uint16 value has 2 bytes, it's just 1024 uint16 values. Okay, they are stored in here. We'll give some notification like, okay, this is transfer number, blah, blah, blah. And then down here, this data will simply be plotted. And then this count variable will be incremented so that it will do this for some time. And here it will send this S message again. I have not run that script. I want to maybe do that today or tomorrow to simply check what this is all about. And then the cycle simply continues for 11 times. So in total, there should be 11 measurements. Or 10. 10. Good. This is approximately the storyline. Are you still alive?
Yes, Professor.
Yes, Professor.
Professor, just one question. This means that the ADC number of samples from the ADC should be equal to 2048 bytes.
No, you want to have 1024 samples, where each sample is a 16-bit value.
Okay.
Yeah. So if we have a look, I'm not an expert with this Delta Sigma ADC, but I saw that Professor Banvard did a little bit about it in his lecture, so please refer to that. If you say that the result of this should be 16-bit, right, then each sample, of course, will be 16-bit. And if you store this in an array like that, right, and you have 1024 samples, then the overall size is 2048. Okay. No more questions?
Professor, just one question regarding this ADC configuration. There was like now, for example, the ADC should be working on a continuous mode or a single-ended mode for getting this 1024 samples. Like, do we need to continuously monitor the data?
Well, I don't want to dig too deep into this right now because this is part of your assignment. So think about how you have to configure that. Yeah. I would say from a user perspective, I'm not sure if this is possible with this configuration, but I think it would be very handy that you just give one single start now thingy, and then it will automatically produce those 1024 samples. Yeah, this would be desirable. Yeah?
Okay.
And of course, you also have to think about if you want to do this automatically, how often you want to have new samples, right? So that you can capture, for example, your entire waveform. Yeah? So this actually would make sense that you try to capture just one or like a configurable number of waveforms generated by the wave deck, and a single wave will not make sense for the how's it called, for the bandpass filter. There you need more samples
Okay.
to simply see how this behaves. Yeah, but for now, like, we just want to have our test bench somehow working. Okay. Okay.
So, Professor, is it something like from the DAC we are emulating the sensor and we are sending this analog signals to the ADC, which is doing our sampling, and then sending this information to MATLAB, and
Exactly.
then okay, and then the MATLAB does some FFT and stuff, which will tell us the desired output.
I mean, like, I'm not sure where Professor Banvat wants to go with that, but I mean, like, you can do multiple things with that. So, for example, you could test the characteristics of your amplifier. You can give a stimulus with the wave deck, and then in MATLAB, you can simply check the waveform or the characteristics and see if this is what you want. Another idea could be, like I mentioned already in the beginning, you could perform an FFT on a signal with the PSOC and transmit this information to MATLAB to simply visualize it, but also perform an FFT of the raw data in MATLAB and then compare those two FFTs to check if the FFT on the PSOC works correctly, for example.
Okay, so something like benchmarking we can do, like on this
Yes.
hardware, how perfect it is. Okay.
Exactly. Because we do not have the radio sensor itself, we simply simulate it with the wave deck. So that's a little bit the idea.
Okay, Professor.
Yeah, but I think for this assignment now, as I have read it, I mean, like you can maybe discuss this again in the lecture or whenever you have the chance for that. But I think now it's rather simple and more about like the data flow with the wave dark and the delta sigma, the DMA, and pumping that into MATLAB. This is a little bit the story here.
Okay, okay, Professor.
Professor, are we allowed to use Erica for the designing, or is it like we should use
Sure.
the normal?
As
Okay.
long as it works, I personally do not care.
Okay.
No, but you should ask yourself if this, I mean, like if you just want to play around and you feel like I can do it, perfectly fine. But you always should be aware that you bring in some additional complexity which might cause problems. Yeah, but this is up to you. Your responsibility. You are the engineer.
Sure.
Okay. Good. So if there are no more questions, I would like to close this meeting now. Of course, you are welcome to ask questions by mail, for example, or using the Moodle page.
Okay, Professor, after doing certain analysis, can we like join the other group if
Sure.
we have some other problems?
Sure,
Like in the next
of course. Of course.
Okay.
You have the link already?
No.
Should have. No? Okay. Then
We belong to Thursday X group, so we have the link only for the X group.
okay. Yeah, wait a second.